Okay, I hope you've given a try to this first set of homework problems. We're going to look at 423 to 430, and I've got the answer key here, and I'll give you a little bit of commentary. And, if you got some of them, great. If you weren't sure how to do them, great. Learn from the key, and we could go forward. There's one more section of Chapter 4 I need to handle, and I'll work on that later today. So in 423, we're doing a problem that considers an absolute molar entropy being used as the foundation to calculate a delta S of mixing, and then ultimately what's the absolute entropy for the mixture. So you could look up in your appendix the absolute molar entropy for lots of substances. Here we have molecular oxygen and molecular nitrogen at 25 degrees Celsius. So what's the mixture of 2.4 moles of oxygen and 9.2 moles of nitrogen? The delta S of mixture equation, 417, will give you the increase. If you want to know the absolute entropy of the whole mixture, you need to add this term to the original entropies from the pre-mixture case. So what do we need to do? So we need to calculate mole fractions. As you can see inside the formulas, we need the mole fraction of each of the components as part of our step. So I took the mole fraction of oxygen. I kept an extra sig fig as an intermediate step, and then to round off later, we'll do that. So I plugged in the mole fractions, the numbers of moles. Notice that the equation has an R and a negative sign. Now, remember that since mole fractions are numbers between 0 and 1, those natural log terms are going to give a net negative for those individual terms, and ultimately the delta S of mixing is a positive value. That makes sense, right? When you mix together pure substances, the final condition is going to have more disorder than they started at the beginning. So we fully expect that value to be positive. You can calculate the final entropy of the entire system by adding that term to the initial entropies. We had 2.4 moles of oxygen and 9.2 moles of nitrogen, and add that to the delta S of mixing term. And I rounded this to 2 sig figs ultimately, mostly because of what the initial numbers of moles were. So again, nothing to get too upset about, but I noticed that in this section, the answer key was attentive to sig figs, so I'll do my best for that here. And that's what I got, 2.3 times 10 to the third joules per kilogram. The next question, 24, says I have 0.54 moles of steam, and it undergoes a cyclic process for which the total heat is negative 74 joules. What is delta S? Well, it really doesn't matter what the quantitative values were for these conditions, other than to say the key word here is that it's a cyclic process. So like the Carnot cycle, or really any engine or motor that is operating in a heat engine context, any cyclic process for any state function, since the initial and final states are identical, the delta S or the delta U or the delta H is going to be 0. Now the Q's and the W's are going to be dependent on the individual steps, and you could calculate those, and those are not likely to be 0. But for the state functions, all you care about is that it's a cyclic process. Predict if the delta S, or really I should have written here the delta S of the reaction, is positive or negative. Here I have 4 moles of solid and 3 moles of gas going to 2 moles of solid. Now, since I have no gas on the right-hand side, this is definitely becoming a more ordered system. So you would expect the delta S of the reaction to be negative. We have less disorder. Same thing here. 2 moles of gas going to 1 mole of gas, I would expect less disorder. A mole of solid decomposing into gas, you would expect more disorder, a positive delta S. Here we have 2 moles of gas going to 2 moles of gas. Not knowing the values, the quantitative values ahead of time, I would just say that it's going to be fairly close to 0. Now we can calculate these values by looking at numbers in the back of the text in the appendix. And so that's what I'm going to do right here. I'm going to use values from Appendix B to calculate the delta S of reaction for the reactions in the previous problem. This just is a matter of being careful and using the correct coefficients from the balanced reaction. And you can see that both A and B give negative values of the delta S of the reaction. The systems became more ordered. The third reaction was the one where the solid went to gas, and you expect a relatively significant positive value. And then the final one, when we had 2 moles of gas going to 2 moles of gas, this number ends up being a small positive number. Now, you could see that since you have a heterogeneous diatomic instead of homogeneous diatomic, that's probably a way in which you're having more disorder there. And so probably if you thought more deeply about it, you could have predicted that the near zero value would be positive. But in general, these all conform to the predictions from the earlier slide. In 427, I have 0.35 moles of an ideal gas at 15.6 degrees expanding from 1.2 liters to 7.4 liters. So calculate this string of thermodynamic functions when carried out first isothermally and reversibly. Well, by now, you should realize that some of these trigger words give you the answers inside the definitions of the words, like an isothermal change of an ideal gas has no change in internal energy. The Q of the system is going to be equal to the opposite of the work, or vice versa. It's easy to calculate the work. We did that back in chapter 2, I think. For a reversible expansion of an ideal gas, you get minus nRT times the natural log of V2 over V1. And when I chug that through, I get a negative 1530 joules, or rounding off to 3 sig figs, I get minus 1.53 times 10 to the third joules. Again, I wouldn't get hung up on sig figs, but I was just kind of following their lead here, keeping 1 extra sig fig along for the ride until the very end. The value of Q is going to be the opposite. That makes sense, right? When we did expansions and you're doing work, the system loses energy, and so heat energy is going to come in from the surroundings. That exactly matches that. The definition of the delta S of the system here is going to be the Q that is exchanged in the reversible path divided by T, and I get a value of 5.3 joules per Kelvin. Now, what about these same thermodynamic terms if instead of being reversible, the expansion happened all at once against a constant pressure of 1 atmosphere? Well, since it's isothermal, the delta U is still 0, and Q is still equal to minus W. But now we have a different equation for the work. You should know this one. It's minus P external times the change in the volume. I chug that through, and I got a value of work of minus 628, and the Q is plus 628. Remember, a irreversible expansion is going to do less work, and it's going to take in less heat from the surroundings. However, the delta S must be the same because it's a state function. A delta S compares the final state to the initial state, and our path to that answer requires us to use the reversible conditions to get that value. So it has to be calculated using a reversible path. If you need to review that, that's in the beginning of chapter 4. What about 1 mole of ideal gas expanding isothermally from 5 liters to 10 liters at 300 K? Let's not just calculate the delta S of the system, but also the delta S of the surroundings and the delta S of the universe. So what's our path there? Well, first, let's do it reversibly. Remember, that's the way that's going to get us inside delta S's of systems, doing the reversible path. That was derived in equation 4.3, and you could do it doing the work in Q way like we did in the previous problem, but we do have a more direct equation, and that is equation 4.3. Equation 4.3 yields a value of positive 5.8 for the delta S of the system. You would expect a system that has a larger volume to have more microstates, so there's more disorder. The delta S of the surroundings is minus 5.8. Again, why? Because this was done reversibly. Any heat that flowed in is exactly the amount of heat that came to it from the outside, and basically, again, this comes out of the definition of reversible, is what I should say. The delta S of the universe of any reversible process, by definition, is 0. But what if the change happened irreversibly against a constant pressure? The delta S of the system is constant because it's a state function. The delta S of the surroundings is going to require you this time to figure out the exact Q flow. The Q of the surroundings can't be determined unless you first find the work that was done by the system. The work that was done by the system, you use your minus P delta V, I get minus 1010 joules. Because this was isothermal, the Q is going to be a positive value, a positive 1010. And I am, let's see. Yeah, I jumped the gun there a little bit. So this value is the work of the system. And so the Q of the system would be a positive 1010 joules, right? That's the heat that flowed into the system to make up for the work that was done. The Q of the surroundings is going to be the negative of that, and so that's why this numerator ends up being negative. Again, the surroundings lost thermal energy, so that's a negative value. If you divide by the temperature that the process occurred, you get a delta S of surroundings of minus, the 3 sig figs minus 3.37, the 2 sig figs minus 3.4. I should have left it the extra sig fig. So therefore, the delta S of the universe is going to be the delta S of the system, which we calculated above, and then transferred to set problem B, and then I add the delta S of the surroundings, which is a negative number, and this ends up being the delta S of the universe. Irreversible processes that are spontaneous are going to have positive delta S's of the universe. That's inherent in the second law. 4.29 asks us to calculate the delta S of a system, delta S of surroundings, and delta S of the universe for a heating process with a non-constant heat capacity. So we're given we're given the polynomial for heat capacity of hydrogen here. Let's figure out the delta S of the system. We've actually done this already. If you look at page 148 in problem 419, little ds, remember, was equal to dq reversible over t. If you want to find it for a quantitative amount and you turn it into a delta, you have to do the integral. And so the integral is of the definition of Q, which in this case is going to be the moles times the molar heat capacity. Since we have the polynomial gets inserted. You have to be careful. There's some canceling here because the polynomial has a t in the second term. And so I split this up into two pieces. So I'm taking the integral of basically dt over t, which gives me a natural log term. And then I'm taking the integral of dt, which gives me a term in t. Evaluated from 600 to 300, and I get a relatively small value, not a very large increase in entropy. Remember, all I'm doing here is I'm heating hydrogen gas, which is already pretty disordered, and I'm just raising the temperature from 300 to 600. So not a large increase in disorder there. It will occupy more microstates because the volume is increasing. You're making the assumption that you could think of this as being like in a balloon or something. The delta S of the surroundings has to be the negative 1.7 because this was reversible. Reversible processes have equivalent values of the surroundings and equivalent magnitudes of the system and surroundings, and delta S of the universe for a reversible process is 0. We've already touched on that. For B, what if I did an irreversible heating? Well, S is a state function, so therefore the delta S of the system has to be the same, 1.7 joules per K. This is a different version of the one we had done a little earlier with the reaction. Now, the delta S of the system was calculated using a reversible Q. In this problem, we have to find the delta S of the surroundings once we calculate the Q of the surroundings in this irreversible context. The Q of the surroundings is the negative of the Q of the system. Since we're assuming this is a constant pressure, like I said, in a balloon, I'm just heating a balloon, Q of the system is going to be the same as delta H. So you can make a substitution there. So notice here that when you're doing the integral, you don't have the t in the denominator because you're finding the Q over this range, not the delta S. So the same heat capacity polynomials used, but the integral is a bit different than the one you just did. So that's why you end up having a slightly different polynomial to look at here. You could put them side by side and look at the difference. I think you should be able to do this. Again, you do the integral, which I did. I kind of skipped a step in there to save some space, and evaluate it from 600 to 300, and I get a value of Q of the surroundings is minus 763. The delta S of the surroundings is the Q of the surroundings divided by the temperature at which the process occurs. Now let me think here. Why are we doing this at 600? Yeah, I think this is something I need to look into because the heating occurred from 300 to 600. I'm not 100% sure because that heat flow out, and let's see, in this case we're heating, right? So we're the surroundings is losing thermal energy. That loss of thermal energy is not all happening at the same temperature, and so when it says it's irreversible, I don't know if there's an interpretation there kind of saying instantaneously you're taking someone at 300 K and then putting it in a 600-degree oven. I guess you could think of it that way. If you think of it that way, then the heat flow is happening from the outside, which is 600 K. When you do the division, I end up getting, and again, I might be sloppy with sig figs here, minus 1.27 joules per K. You could round that off. Overall, I noticed in the key the answer was 0.5. So again, this might be a little sloppy. I'm going to double check it after I submit this to you guys. And then 4.30 asks us to do a similar calculation for a reaction. This reaction is a mole of nitrogen and a mole of oxygen going to 2NO. Calculate the delta S of the reaction, the delta S of the surroundings, and the delta S of the universe. The delta S of the reaction is just pretty much getting numbers from the back of the book in the appendix and being attentive to stoichiometry. So it's products minus reactants. You get a delta S of reaction of a positive 24.6. This kind of mimics what we did a little earlier when we mixed together, I think it was hydrogen and chlorine to get HCl. We get a small positive amount of disorder because we're going from homogeneous diatomics to heterogeneous. For the delta S of the surroundings, you need the Q of the surroundings, just like the previous problem. Since we're going to assume constant pressure, we could use delta H again. Now, in this case, the delta H of this is for a reaction. And the delta H of the reaction is just going to be products minus reactants using heats of formation from Appendix B. The fact that we have got elements here makes our life a little easier, and so we get a delta H of a reaction of positive 180.8 kilojoules per mole. Keep an eye on your units. The delta H of the surroundings is going to be the opposite of that, because that's what we're after. We're after the delta S of surroundings, so I need the delta H of the surroundings over the temperature at which the reaction occurs. Delta S's are usually written in terms of joules per K per mole, so that's why I popped out the 180 kilojoules to 180,000, and I got minus 607 joules per K per mole. The delta S of the universe is quite a negative delta S. That means that if this reaction occurred, because it requires so much heat energy from the outside because this reaction is so endothermic, it would create a large amount of ordering in the universe. And so I say yay for Earth here because this reaction is not close to being spontaneous. Think about our atmosphere if that reaction was spontaneous. There's 80% of the air around us is nitrogen, 20% is oxygen. That would be bad since we need oxygen to live. So I hope this was helpful. I'll work on the last section later today, see how the day goes. Hopefully I can get it in the books today, possibly in the morning. So hope everybody's doing well. Take it easy.